Hi everyone. In this session we're going to do a very general overview of the RISC-V architecture. First off, we'll do an overview of the RISC-V architecture. We'll look at the design goals. We'll look at the application domains, and then the RISC-V register set. Now this textbook that we're using, the let-in textbook, puts a whole chapter on the RISC-V architecture, but we're running out of a little bit of time in this course, so I'm just going to go through a really kind of general overview of the RISC-V architecture. So it's relatively new compared to the other architectures we've been looking at. It was publicly announced in 2014, so less than 10 years ago. And it was developed at a very prestigious university in the US, at the University of California, Berkeley. And it followed 4 previous RISC design projects, hence the V, which stands for in Roman numerals 5. So it's the RISC-V project. And the main goal was to design a RISC instruction set, so reduced instruction set architecture for use across many applications. And one of the big advantages that this group had over, for example, AMD and Intel decision making is that they didn't have to think about or worry about any legacy. They could basically design from scratch. So incorporating all of the technologies that have been incorporated, all of the architectures that have been created up until 2014, they could kind of pick and choose the best parts of those and create an architecture from scratch. So they wanted to do this from micro-powered embedded devices right up to high-performance cloud servers. So the main design goals were to provide a freely usable ISA for any application, so an instruction set. And this contrasts with all other proprietary commercial processors. Like I mentioned, the architectures designed by Intel are designed to work specifically on certain types of hardware. So the other design goal, another design goal, is to incorporate lessons learned from, again, decades of processor design. So they could basically cherry pick or take the best parts of previously designed architectures like the Intel architecture and the AMD architecture, and use that as a foundation or a basis to create their own architecture. So they can start clean without any of these legacy capabilities. Huge advantage. And then to provide a small, complete base architecture for use in embedded devices. So as we've moved forward in time, these embedded devices have become much more popular. For example, devices like smartwatches. Also, one thing we haven't talked about much in this course, but which is, of course, becoming more and more prevalent in society, is this IoT, or Internet of Things. So these devices show up in things like refrigerators and shoes even, to be able to record data and provide that data to some sort of a central location for processing and analysis. So these embedded devices require very, minute or very small processing capabilities on very low power, in very low powered situations. Now, all instructions for the RISC-V are 32 bits long, and the base instruction set supports addition and subtraction, but not multiplication and division. So again, very simple. And this avoids expensive hardware requirements. Also, they wanted to provide optional instruction set extensions to support more complex calculations. They have the ability to kind of add these things on as required, but start very simple as a foundation, as a core, and then be able to add on what they call extensions to add more complex calculations. So for example, floating point math, atomic memory operations, multiplication, division, that would all be as part of an extension rather than the core. So the core could be used in, for example, low power, low processing situations, but if you wanted to scale up to something much more processor intensive, you can add on these extensions to do that. So basically a flexible architecture. Also to provide additional ISA extensions to support privileged execution modes, so in situations where security is more of an issue. And this is similar to the x86 and x64 and the ARM privileged implementation. So again, not part of the base architecture, but fairly easily added onto using an extension. Also to support a compressed instruction set, so implementing 62-bit versions of 32-bit instructions. And again, this is with the idea of resource-limited situations where you want to try and condense code into smaller memory spaces, right? So 16-bit, of course, if we're designing code that's 16-bit, it takes up half the space as 32-bit code. Also to provide optional ISA extensions to support 64-bit, so going the other direction, also 128-bit processor word sizes. So again, that ability to scale from very small devices up to very large and processor-intensive devices and architectures using these extensions. Also page virtual memory on single and multi-core processors, again, scaling up very well with the extensions. So today RISC's processors are available on the market, and they're in a lot of devices. They're comparatively priced. Market share may grow due to the advantage of its free-to-use nature. So anybody who's designing a device has access to that architecture. And RISC-V Linux distributions are available, and it includes software development tools needed to build and run applications on RISC-V devices. Some applications where we're seeing it, where RISC-V devices are actually being used. Artificial intelligence and machine learning, very math heavy, very processor intensive. Also in embedded systems. Extreme scale computing. So again, by extensions, we can scale up. So we can see these architectures in applications on supercomputer platforms. And then right at the other end of the spectrum, also ultra low power processing. So allowing battery operated devices to run for months on a single charge. So IoT devices is an example. So let's think of a weather monitoring station. So you have weather monitoring hardware that can run in very low power environments, maybe just off of a solar panel using RISC-V architecture, can run for a very long time on very limited resources. And then processing at the IoT edge, so the ability to interface with Internet of Things devices, to do AI, also to do data encryption on these sort of devices. So we see RISC-V architectures in a lot of these applications. The register set, 31 registers are each 32 bits wide. General purpose registers X1 through X31, we can see them here across our diagram. They can be used with no restrictions. The PC register, which is the register shown at the top singly here, so this is the PC register, contains a program counter, of course. Sorry, next. Oh, it uses a 3 operand format. What do we mean by that? Well, if we look at this addition here, we can see that X2 here is added to X3. And then the result is stored into X1. Okay, so that's what we mean by the 3 operand format. So we do a calculation on X2 and X3, and then we store the result of that in X1. Now, if we look at some of the registers over here on the diagram on the right, the RA register, so this register here, is function return address. So if we make a function call and we return back to this particular register. The stack pointer, you can see, is the next one in line here, right? So it indicates where we are on the stack. So it'll increment and decrement accordingly. We have the global data pointer. We have the thread data pointer. And then we have a bunch of registers that are temporary storage. So T0 to T6. So here's T0, T1. And then way down over here, and T2, sorry. And then way down over here, we have T3, 4, 5, and 6. So these are temporary registers for temporary storage. And then we also have the frame pointer here for function local stack data. And then A0 to A7, so A0 starting here, A7 finishing here, so all kind of in sequential order. Arguments are passed to functions. Any additional arguments are passed on the stack. And function return values are passed in A0 here and in A1. So this is just a quick overview of the RISC-V register set. Oops. And that's really all I wanted to talk about in this particular session. Just a quick overview of RISC-V. Look at the design goals. And again, one of the big advantages of designing in this way with the RISC-V was in designing it more recently in 2014 is that the designers could design the architecture, the RISC-V architecture from scratch, taking the best of all the previous architectures, x86, 64, and ARM, to design an architecture that was very flexible. Some of the application domains where we see RISC-V, and then lastly, just a quick look at the registered set. Okay, so thanks for tuning in. We'll see you in the next session.